So remember, let me recall what we were doing last time. We gave another representation of TSS CPPs, this time as triangular arrays. So what we did was we chopped off 1/12 of the TSS CPP and we counted the heights of boxes in that region, and we sort of subtracted subtracted every entry from n+1 in general, and we rotated by counterclockwise by pi/2, and we obtained a triangular array. And I claimed that these are in bijection with these triangular arrays satisfy the following conditions. So in the ith row there are n-i+1 entries, and they are arranged in this way. They are weakly increasing along rows, weakly decreasing down columns, and the jth column, the entries in the jth column are less than or equal to j, and all entries are positive integers. Okay, so this was what we said last time, and let's now construct all. So let us construct all Magog triangles of order 3. So what are they going to be? So as I said last time, the first column is always supposed to be all ones, and so let's start with this simplest one. So you can have all ones throughout, right? Because you just want weak increase along rows and weak decrease down columns, and entries here in this column should be less than or equal to 2, here should be less than or equal to 3. Okay, the next one is 1, 1, 1, again 1, 1. I can put a 2 here, and similarly I can go up to 3 here. Right? So the entries here are less than or equal to 3. Okay, so that's 3. Okay, so now let's start tweaking these entries. So the next entry I can tweak is this one. So if I have 1, 1, 1, I can make this a 2, 1, and then because of the weak increase, this has to be at least 2, and then I can do a 2, 1, and then a 3. And okay, so I need 2 more, and I can do that as follows. I can now tweak this entry, so I cannot make this larger than 2, remember. So then I can, if I make this a 2, this has to be at least a 2, but this can be at most a 2, then this is fixed, and then I have the last one, which is this. Okay, so these are the 7 Magog triangles of order 3. You can see if you don't have any other choice. Okay, so let us compare now with these 7 TSS CVPs of order 3. So I will, for each of those, I'll write the height function. I'll write the corresponding heights. Let me make it smaller. since you've seen it before. So remember what we are doing. So compare. Oops. So compare with 70 CPPs in 6 by 6 by 6 box. Okay, so in the same order, let me write the heights. So remember, I'm looking at the heights in maybe I'll mark it with red. So I'm looking at the heights of these boxes: 1, 2, 3, 4, 5, and 6. Okay, and so here I have so I have 3, 3, 3, 3, 2, 2. Then I have 3, 3, 3 over here, 3, 2, 1, and over here I have 3, 3, 3, 3, 3, 1, is that? And here I have 3, 3, 3, 2, 2, 1, and here I have 3, 3, 3, 2, 2, 2, and here it's 3, 3, 3, 3, 3, 2. This is not the same as this. Notice this difference. And the last one is all threes. And now if you subtract by 4, if you subtract every entry by 4 and rotate counterclockwise, I claim that you will get these 7. So for example, let's take this. So I'll not do all of them. So let's take this. Circle. So subtract 4, and so you get 1, 1, 1, 1, 2, 2, and then rotate counterclockwise. So you get 1, 2, 2 for the last column, 1, 1, and 1. Right? So that's this. So similarly, you can get all. Okay. So right. So what we have done is to so modulo. So maybe I'll write that as a proposition. Magog triangles of order n in natural bijection with TSS-CTPs in a 2n by 2n by 2n box. Right, so this is a good encoding. And now I recall something that we had proved a long time ago. That we had shown that monotone triangles are in natural bijection with ASMs. And so let me define these again. So now using Zeilberger's terminology, we'll say that a monotone triangle gog or a monotone triangle of order n is an array Gij, G for gog, 1 less than equal to j less than equal to I less than equal to n of positive integers satisfying. So I had defined this earlier when we were talking about Aztec diamonds. So what are the properties? So 1 is less than equal to Gij less than equal to n. Gij is less than or equal to Gi minus 1j is less than or equal to Gij plus 1. But Gij, the two entries over here, satisfy a strict inequality. Remember, if I don't have this condition, they only satisfy weak inequality, and in that case, these are called Gelfand-Settling patterns. And Gnj is j. So these are arrays of this form. So G11, G21, G22, etc. Gn1, Gn2 to Gnn, and you have inequality of the form. Any entry over here is less than or equal to the entry above in this diagonal, whatever it's southwest to northeast diagonal, and it's less than or equal to this, so that is weak increase along the northwest to southeast diagonal, but a strict increase here, and the bottom entries are frozen. Okay, and the way we constructed these was from ASMs was to sum all the columns up to row I and read off the entries, read off the column entries which are 1. So just to recap, the gog triangles of order 3 are as follows. So you have 1, 1, 2, 1, 2, 3, 1, 1, 3, 1, 2, 3, 2, 1, 2, 1, 2, 3, 2, 1, 3, 1, 2, 3, 2, 2, 3, 1, 2, 3, 3, 1, 3, 1, 2, 3, and 3, 2, 3, 1, 2, 3. Okay, so as you can see, they are weakly increasing along these diagonals, up these diagonals, and down these diagonals, and strictly increasing along. And so, as I said, Zeilberger called this gog triangles, and he called the other ones magog triangles because I don't know, these are two tribes in two warring tribes in the Bible. So somehow the name has stuck. And the ASM conjecture is the ASM conjecture, which is that the number of gog triangles of order n is this given by this product formula, nice product formula, can be reformulated as saying number of gog triangles of order n is equal to number of gog triangles. Right, so this is the reformulation that Mills, Robbins, and Rumsey came up with. So due to okay, so now let us pause a bit and compare these two triangles. So for the gog triangles, you have this kind of inequalities and the bottom row frozen, and for the magog triangles, you have yeah. So for the magog triangles, you have inequalities which are of a different flavor. So they are weakly decreasing down here, weakly increasing down here. But the funny condition is this, that the entries in any column in the column J are less than or equal to J. So I have, the way I have drawn it is the triangles look different, but they are, you can of course rotate them and get them in the same shape. So each one of them has whatever and choose two entries, and the bottom row or some row or some column is frozen of length n in both, and so you think, come on, I mean, this has to be, there has to be a bijection. This is ridiculous, So lots of I have not gone into this, but lots of statistics are also equal, and so there's a strong temptation to imagine that these two, I mean, there should be a bijection. Unfortunately, there does not seem to be an easy bijective proof. Okay, but there are several kind of partial bijections in the sense that for a certain subset of certain subsets of gog triangles are in bijection with certain other subsets of gog triangles, magog triangles, and but there is nothing that works for all of them. So I mean, so it's kind of tantalizing open problem. So it's quite elementary, but we seem to require deeper ideas. Yeah, this whole subject, even though is can be framed in a purely enumerative way, I mean, all the proofs seem to require much more high-powered machinery, which leads one to suspect that there is really something deep going on here. So let me also say that there are further statistics that are common between the two. So I'll not go into it too much, but just as I mentioned in the very beginning of the course, that there are statistics relating. I remember I gave you 4 statistics for ASMs and 4 statistics for descending plane partitions, and the number of objects on both sides fixing those statistics are the same, and there is a proof, but non-bijective. I mean, that suggests that there has to be a bijective proof, but several people have tried very hard, and only partial results are. Okay, but I want to show you some more results and conjectures which it suggests that there has to be some unifying idea which we don't have yet. Okay. So let me generalize this further, and this is already due to Ms. Robbins Rumsey. So definition. An NK gog trapezoid. This terminology again is due to Zeilberger. Is a gog triangle of order n. In which only the first k what is it, south west to northeast diagonals are kept. So let me give an example of a 5-3 gog trapezoid. So so 4, 3, 5, 2, 4, 5. So up till now it looks like a triangle, but after this you only keep rows of order of length 3. 1, 3, 4, 1, 2, 3. Because of the gog triangle condition, the bottom row will be 1 through k. In this case 3. Okay, so you have chopped off a 3 by 3 triangle. That's another way. Sorry, a 2 by 2 triangle. I mean order 2 triangle from the right. Okay. Yeah, please ask if there are any questions. On the other side, an NK magog trapezoid is a magog triangle of order n, in which only the first k, topmost k rows are kept. So let me give an example, a different example. A 5-3 gog trapezoid. So what we'll do is we'll keep the first topmost k, in this case 3 rows, intact. So 1, 2, 3, 3, 5. 1, 2, 2, 3. 1, 2, 2. Okay. So what we have done is killed this bottom, but here, just like over in the gog trapezoid, the first k entries. The first entry in the first entry in the first k, in the k columns, in the k rows are present. So these ones are fixed. Sorry, let me say that again. So the first column is preserved, is fixed to be equal to 1. Just like here, the bottom row is fixed to be this increasing sequence of 1 through k. Okay. All right, so this is the theorem that Zeilberger proved, conjectured by Ms. Robbins Rumsey in the 80s, I forget the exact date, due to Zeilberger. 25. So the number I should have said for 1 less than equal to k less than equal to. So if k is equal to n, then this is a gog. And here too, for 1 less than equal to k less than equal to n. If k is equal to n, this is a magog triangle. Okay. So what Zeilberger proved was that the 1 less than equal to k less than equal to n, the number of nk gog trapezoids is equal to the number of nk gog trapezoids. Okay, so so when k equals n, or by setting this proves the asymmetry. Okay, so I wanted to show you some examples on Sage, but unfortunately, well, I wanted to show you some examples numerically, but unfortunately, even for small sizes, unless things are trivial, one gets very large numbers. So, for example, one trivial example is notice that k equals n minus 1 is also follows is implied by k equals n. Because if k equals n minus 1, that means you are only removing the last entry over here, which was an n anyway, which was forced. And over here, you are only removing the last column, which contained a single 1, which was also forced. So, so then, and gives the same also. And is also enumerated by n. So, so going back to this example, if I just chop off the 3 over here, I'll get 7, 3 2 gog trapezoids, and deleting the 1 at the bottom row, I'll get the number of 3 2 magog trapezoids to be also set. Okay. So I want to mention the I want to give you the flavor of the proof idea. I mean, we won't be able to go in detail, but at least we can see the starting point. And but before I do that, I want to mention another generalization. So more generalizations are conjectured. And I want to give you one of them. Okay, so before that, maybe I'll show you this one. So I have already written programs for this in Mathematica. So rather than constructing them in Sage, which would take some time, let me show you. So let me show you this. So I encourage you to program these guys. So these are the k-gog triangles. As I said, these are exact of these are the 3 2-gog triangles. Forget this middle parameter for a moment. I'll introduce that shortly. But these are exactly these with the 3 loops. 1 1 2 1 2 1. So bottom is always 1 2, and then the other 2. The top is arranged this way, and the 3 2 gog triangles are these ones. So all ones, then a 2, then a 3, and 2 2 3. So these are these. Okay. So but one can go larger. So if I do 4 2, so this 3 2 is kind of trivial. So now you see they start to get more complicated. And there are many more. And so let me show you some non-trivial. Let's just see that the lengths are equal. So lengths, let's say n0k equal to n0k. So let's go n going from 2 to 5. I don't want to go very high, but I want to show you that it is non-trivial. So k going from 1 to n. You see there. So I'm just saying that these two lengths are equal, and it will return to. I think I can go to 6, but okay. Yeah. So. And just to show you that the lengths are really non-trivial, so maybe just write a new line. You see, the numbers are can be really huge. So it's really a non-trivial check. And as I said, you can try for a bijection, but this seems to be genuinely difficult, and whatever ideas you try for small sizes sort of start breaking down when you go higher, and you start having to make larger and larger tweaks, and ultimately it goes out of hand, and you're not able to see the structure. So even for size 7, there are, as I said, there are more than 200,000. Let me leave this running. It will be too long, I think. So at that point things become very unfeasible. But who knows? It's possible that there is a nice bijective proof, but people have not found it. Okay, so now I want to mention the new generalization. So here's the definition. So an M and K. Okay, so this one is done. So now you can see they are really massive numbers, and we let the transformer gog run. So an M and K gog trapezoid is a trapezoid of integers arranged as an nk gog trapezoid satisfying the same inequalities such that the entries in the ith southeast to northwest diagonal are bounded above by m plus I for 1 less than equal to I less than equal to I. So it's an nk gog trapezoid and m is an arbitrary integer. M and n can be 0 and 1 less than equal to k less than equal to. Okay, so here's an example of a 375 trapezoid. So here it is. So it's a 7-5 gog trapezoid. It has that shape. But the 3 is going to kick in later. So 4, 3, 5, 2, 5, 8, 2, 4, 7, 9, 1, 4, 6, 7, 10, 1, 4, 5, 7, 8. Now bottom row is 5. And now the last row is not 1, 2, 3, 4, 5. And that's where you have the freedom. So 1, 3, 5, 6, 8. Okay. So when I say it satisfies the same inequalities, I mean this inequality is like this. But the bottom row is not bounded. Does not respect bottom row, and this diagonal does not respect the same inequalities. So for example, this is here. So this entry is less than or equal to 4 because this is 3. 1 plus 3. The first diagonal is less than or equal to 4. This is less than or equal to 5, 6, 7, less than or equal to 8, less than or equal to 9, less than or equal to 10, like that. So the entries which are maximal are this 8 and this 10. Okay, so all other entries. So these are the maximal entries. Right? So you cannot go above 8 here. So this kind of saturates that inequality. Okay, and similarly, definition. So these an MNK Magog trapezoid. Oh, I should have highlighted this MNK Gog trapezoid. Again for an arbitrary and k between 1 and n is a trapezoid of integers, blah blah blah, same thing. Arranged as in an NK Magog trapezoid. Satisfying the same inequalities such that the entries in the ith column this time are bounded above by m plus I. So here's an example again of a 275 gog trapezoid. So 3, 3, 4, 5, 7, 7, 9. 2, 3, 4, 5, 6, 7. 2, 3, 3, 4, 4. 1, 2, 3, 3. 1, 1, 2. So it has 5 rows. That's the 5. And so now notice that the first column does not satisfy this, the condition that, I mean, is not fixed to be 1. There's more freedom. But the other inequalities are the same. So this is weak increase down, weak increase along rows, and weak decrease down, oh, sorry, weak decrease down columns, but this condition. So this is less than equal to, so here m is 2. So this is 3, less than equal to 4, less than equal to 5, etc. Less than 6, 7, 8, 9. So these entries saturate this inequality. This is less than equal to 7, like so. Okay. Any questions so far? So when m equals 0, we get back to the other trapezoid, to the usual trapezoids of Robbins Rumsey. And the reason for defining these, as you can imagine, is a conjecture due to Krattenthaler from 96. So not long after Zeilberger's theorem, that the number of m and k gog trapezoids is equal to the number of m and k gog trapezoids. Again, for 1 less than equal to k less than equal to n arbitrary, and n also arbitrary. Yeah, so really remarkable conjecture, and you know, this suggests even more strongly that there is a bijective. There should be a bijective proof, but people have tried very hard, and if you want to play with it, please feel free. But I suggest that you don't spend too much time, because it's an enormous time sink. Okay. So let me show you again on Mathematica. So that's this, m is this parameter. Unfortunately, my m is not the same. So I mean, it's not, I have not written m and k, rather n and k. But this doesn't bother you too much. So let's look at that. So remember this kind of boring case. Now if I put 1, already there are too many. So I can't write down a small example. This is not too good. And here also I can put 1. So, oh, by the way, the Magog computation is finished for n equals 7. You can see that the numbers match. You know, they're massive. It's not a coincidence. And this, of course, has been proved. But now let me go further. But I'll reduce the size just to make life a little easier. And I'll change m to 1 now. So, okay, so this is also taking to 1. Maybe I should do it for 5. Let's wait a minute, a few seconds more. Okay, so this is way too big. Let's see. So this is m equals 1, and this is n equals 1, and I can compare the two. Let me see what I think I should be able to do 2. Numbers are going to explode. See, already it goes up to 65,000. Right? And you can check for higher. Well, this is already for size 5, and you know, up to size 5, and you know, there's an enormous amount of data which leads one to believe that this conjecture has to be true, but this is wide open. No proof is known, bijective or otherwise. So none of the techniques for the proof of the fact that nk gog trapezoids is equal to nk magog trapezoids seem to work in any straightforward way, although there is some progress. So I should not make it sound completely despondent. The situation is not that bad, but you know, the techniques have not so far worked. So in particular, I should mention Ilse Fischer has made a lot of progress towards proving this, but not proved it. So now let me mention, let me describe Zeilberger's proof again. And this idea, this approach is a subject in combinatorics of constant term. You might have heard of binomial identities. You know, like you know, you have so we call binomial identities of the form. You know, summation n choose k going from 0 to n. Well, I don't have to say that. K going from 0 to n. If k is less than 0, then 0, k greater than n is 0. So one doesn't need to say it. This is kind of easy. We have seen this. Slightly harder identity is this. So what is this? If I sum the squares of the binomial coefficients, does anybody know what the answer is? Okay, this is actually the central binomial coefficient. So, you know, there's an entire area of combinatorics which is devoted to kind of understanding and proving identities of this form. It's kind of gone down over the years due to, you know, computerized proofs of such identities now, due to Zeilberger's algorithm and Zeilberger algorithm. So there are, so literally, I mean, it's not a joke anymore to say that a computer can prove this identity, by which I don't mean prove it for n equals 1, 2, 3, but prove it as an identity. And this is a subject. But just like that, there is this kind of subject of constant term identities, which is less developed. So it began. So the subject began with a beautiful identity due to Freeman Dyson. So the subject of CT. I'll use CT for constant time. With again with Dyson's conjecture. So let me just state it as a result. So this was conjecture. In 1962. So he found this while trying to. He found this identity while looking at something in random matrix theory. But he didn't sort of see a proof, and he, announced it. And it's not terribly hard, but it's such a beautiful result that several people found different proofs. So one of them was due to Ken Wilson. So in the same year, and J. Gunson also in the same year. No relation. But the sort of the nicest, quote unquote, nicest proof is due to Jack Good, who was a statistician. Actually, two of these people are famous. So Ken Wilson won the Nobel Prize in Physics later for his work on the renormalization group. And Good was a statistician who worked initially at Bletchley Park, and he was one of the people who was, responsible for cracking. Worked on Enigma and cracking the codes of the journals. So he later on moved to somewhere in the UK, I forget where, and then he moved to the US. So his original name is a Polish name. He anglicized it to Good. So here's the conjecture, and the theorem. So let a1 up to an be non-negative integers. Then the constant term in x1 up to xn of the Laurent polynomial fn of a1 up to an, which is the following: product over 1 less than or equal to ij less than or equal to n, but I not equal to j, 1 minus xj by xi raised to the aj. Okay, so you take ij distinct, you raise 1 minus xj by xi to the aj power, you expand it out, you will get a huge expansion in general. And now you look at the constant term. So the term which has no power of either of xi or of xi. Or in other words, has the zero power of xi, of all xi's. The constant term is the multinomial coefficient, actually. A1 plus up to an, choose A1 comma up to n. Okay. So it's really beautiful conjecture. In particular, if all the AIs are 1, you get n factorial. So this is the first thing he observed. And then Dyson started to generalize it, and then he found more that you always seem to get the multinomial coefficient. And so several proofs were given, but I'll give you Good's proof, which also is impressive. This is sort of widely considered to be the nicest proof from the book. So the starting point is the following: is an identity. So it's a polynomial identity. So let me show you. So define the polynomial. the polynomial in X depending on distinct indeterminates x1 up to xn as p of x is the sum j equals 1 to n product I equals 1 to n, I not equal to j. So you take the product over all is not equal to j of x minus xi divided by xj minus xi. Okay, and so it's a polynomial in X. I mean, it has all these parameters, and they, they are distinct, so there's no problem with them. Okay. So the starting point is the following. So some of you might have seen such such polynomials in JE type problems. The starting point is the identity P of x is equal to 1 actually, identically equal to. So it does not depend on x. So if you want to see, so for n equals 2, you get two terms, j equals 1 to 2. So the first term is x minus, I can only be 2, so x minus x2 by x1 minus x2 plus x minus x1 by x2 minus x1. And you can see that the x is going to cancel and you will get x1 minus x2. Right? But this is true in general. So this is always equal to 1. Does anybody see a proof, a quick proof? Okay, so let me tell you. So the idea is that first, so there are two ideas. So first, note that px. What is the degree of px? Okay, let's go. What is the degree of this polynomial?
n minus 1.
That's right. So first note that px has degree n minus 1 because in each product you are multiplying n minus 1 terms.
You can plug in the variables one by one and.
Exactly, that's the idea. So it has degree n minus 1. Therefore, it is determined by its values at n points. So that's the first idea. Second, compute p of xi, let's say xk. So what happens if you take x equal to xk? So for all j not equal to k, you will get xk minus xk as one of the terms. And for j equal to k, you will get that the numerator equals denominator. Xk minus xi by xk minus xi. Right? So it's 0 at all but one terms, and in the last term it's 0. It's 1, so you get p of xk equal. So at n points for all k. So at n points it's equal to 1, it has degree n minus 1, and so it's equal to. Thus p of x is identical. Okay, so that's the first point. We'll use that in a second. Okay. So now let's look at Fn. So this is a polynomial. This is a multivariate polynomial in x1 up to xn, which depends on a1 up to an. So maybe the choice of notation is not very good, but this does depend on. This is a multivariate polynomial. Okay, so we'll use this in a second, as I said. Now, suppose a1 up to an are all strictly positive, then compute Fn of a1 up to an. Okay, so okay. So then compute the following sum. So sigma j equals 1 to n Fn of a1 up to a j minus 1, a j minus 1, a j plus 1 to a. Okay, so you have subtracted 1 from the jth element, which you can do because all are strictly positive, and you compute this sum. Okay, so what is this equal to? So everywhere you'll have the same term. It'll be the same as an, except for having one less term when you look at the jth entry. Okay, but what does that mean? So let me take out this, since this is a product, I'll take out Fn common. So this is equal to Fn of a1 up to an, the same things, and now I'll sum. What do I get? What are the other factors? J equals 1 to n. Now I take the product over I equals 1 to n. I not equal to j. And I will get, what is the extra term? This is 1 minus xj by xi raised to the minus 1. So I have to take this product. J is not, I is not equal to j. And in that, for all those i's, I will take one less factor. So that is this factor. Okay. But now I rewrite it as Fn a1 up to an, sum j equals 1 to n, and product I equals 1 to n, I not equal to j. I just rewrite this as minus xi by xj minus xi. Okay? But this thing is nothing else but p of 0. So you look at p of 0, you just plug in x equals 0, you get minus xi by xj minus xi, same sums and products as before, and so this is equal to 1. So what we have shown is that Fn, so Fn as a polynomial satisfies this recursion. So this is equal to Fn of a1 up to a. So we have a recursion for it. This recursion where of order 1 in each variable. Okay, so let C a1 up to an be the, I'll use this notation, this is the constant term in x1 up to xn of Fn a1 up to n. Okay, so this is what we want to compute, and we want to show that this is equal to this multinomial coefficient. Since Fn satisfies this recursion, the constant term also satisfies the same recursion. right? By the argument above, C of A1 up to AN is equal to sum j equals 1 to n of C A1 up to AJ. Everything is the same except AJ is reduced. So the strategy of the proof should be clear by now. We have shown that C satisfies the same recurrence. So this is the same as for the multinomial coefficient. Okay, very good. So that's one part. So we've shown that it satisfies the same recurrence. The second part is to it's kind of easy. It is clear that C A1 up to AN is symmetric in A1 up to AN. Why is that? So I have this Fn. I want the constant term of this. If I sort of interchange Aj and Aj plus 1, I can get the same polynomial by, well, I get a different polynomial by exchanging xj and xj plus 1. But I don't care because I want the constant term, which is already symmetric in the exercise. So just exchange the corresponding exercise. Right? So you do that and you get this symmetry, which is also true for the multinomial coefficient. And the last thing is to show the initial condition. So now suppose AN is 0. Okay, then what happens? Then Fn of A1 up to AN minus 1, 0 is what? So let's go back. So Fn AN only occurs when j equals n. So for I equals 1 to sorry, what do I want to say? So when j equals 1 through n minus 1, we have the same things. And when j is n, this will be all 0. An is 0, so there won't be any contribution. The only contribution will come when I is n and j is anything but n. Right? So is that clear? I mean, if it's not, please ask. So here an will not contribute anything, but when I is n and j is not equal to n, I have to take that into consideration. Right? When I compare with Fn minus 1 of A1 to AN. So I have all the terms in Fn of An up to An minus 1 times there's this product j equals 1 to n minus 1 minus xn by xj. Or which way did I do it? I is n, so xj by xn. Okay, is that clear? But now I want the constant term, right? But this fellow, this does not depend on xn. It's a polynomial in x1 through xn minus 1. That's what this index is saying. So if I want the constant term, so if I want the constant term in xn over here, on the left hand side, must or cannot involve any of the factors xj by xn, because if you pull any single factor from here, you're stuck, because there's 1 by xn will hang around forever, and you cannot kill it by any numerator here, because you cannot kill that xn. Okay, so so you have to take 1 in the numerator, and so that proves that C a1 to an minus 1 0 is equal to C a1 to an minus 1, which is the other recursion, which is the initial condition for the multinomial coefficient. Ultimately, of course, you'll have C a1 0 is C a1, which you can easily calculate. So thus, which is of course which is the binomial coefficient, because if you have a single variable, then you just have 1 power. What am I saying? Yeah, sorry. Then you will get 1, because you'll get a1, which is, and on this side you will get you want the constant term. So if you have only 1 factor, then you cannot take any of these terms. Okay. Thus, C a1 up to an satisfies the recursion and initial conditions of multinomial a1 plus up to an, choose a1 up to an, and so they have to be okay. So let me show this to you on Sage. So this is the Dyson conjecture. So I define this list of variables. So first, let me show you the Dyson polynomial. So here is the Dyson polynomial for in 2 variables with exponents 2 and 1. So a1 is 2, a2 is 1. And so you get x0 by x1 minus 1 squared, x1 by x0 minus 1. This is the usual shift of indices, and now here it is. And you get a 3 over here as the constant term. The other terms are quite complicated in general. So, right. And here is another example in 3 variables. And now you see it's a huge mess. Oh, by the way, that 3 was 2 plus 1 choose 2, which is 3 choose 2, which is 3. And here you have 3 plus 2 plus 1, which is 6, choose 3, 2, 1. And so that is, you can check easily that that's 60, which is the constant term. Okay. So I guess I should have shown you this before proving the result, but it's okay. And you can change the order, and you will get different polynomials with the same constant term. and here is the program which returns the constant term. So if you have all ones, you'll get the n factorial. So if I do 4, 1, I have allowed myself the freedom of choosing more variables, but not less. So I don't. A should not have less than n integers, but it can have more, just to save myself some effort. Unfortunately, there's some problem with Sage, and I'm not able to figure it out. I mean, I'm running the same thing as a loop. For every single value it works, but if I run it over the loop, it gives me some funny error. So it says say has no attribute coefficient. I don't know what the hell is going on. So here what I'm doing is I'm just expanding the Dyson polynomial which I defined earlier, and I am successively taking its coefficient in each xi, and somehow Sage doesn't like it, which I don't understand. So I have what is a bit unsatisfactory is that the variable x is outside, but I suppose I can define it inside also. Okay, what I can do is try defining it over here. It doesn't help. So it gives me some funny error and I'm not able to understand it. I mean, it works for any single n, so I don't understand why it should not work. Okay. So if anybody has any figures out how to fix this, please let me know or post it on the chat. Okay, so I want to, so in the last 10 minutes I want, so okay, so this was in 1962, the Dyson conjecture, and this Good's proof is in 70. And you know, after this, people started discovering a lot of interesting constant term identities, and they started proving it. And you know, this became a sort of minor industry in combinatorics. And let me give you one generalization of Good's identity, which was conjectured by Andrews. So to a Q generalization. So the Q analog was conjectured by Andrews in 1975, and to define this, I don't think I defined the Pochhammer symbol, so let me do it. So the Q Pochhammer symbol it's the analog of the raising factorial. Is defined is a q sub n. This is the product over I equals 0 to n minus 1 minus a q to the I. Okay, so set this way, this looks way too general, but if you set a equal to q, so q is the product I equals 1 to n 1 minus q to the I. So this is, if I divide by 1 minus q to the n, I will get n factorial, the q analog of the n factorial. So nq is qqn by 1 minus q to the n. So this is a natural generalization. It has many terms, but so the theorem due to Zeilberger and Rasool is the constant term in x1 up to xn, and now I'm going to have a complicated looking object on the left hand side. 1 less than equal to I less than j less than equal to n of xi by xj q n. So here notice we don't have I and j running from 1 to n, I not equal to j. Here there are two, I mean we have split it, and there are two terms for each pair ij. Qxj by xi q, oh sorry, not n, ai, and here I have aj. So again a1 up to an non-negative integers. So the constant term of this is the q analog of the multinomial. So it's a1 plus up to an, a1 up to an. Okay. So it sort of generalizes, but you see doesn't generalize in an obvious way. If you had just put q's over there in some brute force way, it wouldn't work. What you have to do is to tweak various q's, and this is part of the problem with q identities. To find the right identity, you have to work a little, because ultimately q is going to be set to 1, so q might be in places that it was not there originally. This happens also for the q binomial theorem. Okay, so so fast forward. So there were a lot of different constant term identities which were conjectured and proved, and so what Zeilberger's approach, so fast forwarding to 93, was to find a way to represent, to count to count both sides using constant term identities, but not the same constant term identity, and this is why this result is quite hard. So let me state Zeilberger's theorem. So Zeilberger's theorem, I'll state it in 3 parts. These are 3 different theorems. This is Zeilberger's theorems. Okay, so the first one is that the number of nk gog trapezoids, I should be able to finish stating this in the rest of today's class, is the following massive constant term identity. Oh, I need some notation for that. So let xi bar, this is not the complex conjugate, this is 1 minus xi. Okay, so this is constant term of x1 up to xn of the product I equals 1 to k, 1 minus 2xi. Okay, so I should write it. Product I equals 1 to k, 1 minus 2xi divided by xi to the n plus k minus I minus 1, and xi bar to n plus k plus 1 times big product of 1 less than equal to I less than j less than equal to k. Okay, so you're not n. There are 2 parameters here, remember, n and k. Xj minus xi, xj plus xi bar divided by 1 minus xij. Okay, so he managed to show that the number of nk Magog trapezoids is this constant term identity. If he had managed to show that nk gog trapezoids are also given by the same constant term identity, then things would have been nice. Unfortunately, it's a very different beast and much more complicated. So let me write it here. So this is constant term again in x1 up to xn, same notation. minus 1 to the k, some big function phi k of x1 up to xn divided by product I equals 1 to k xi to the n xi bar to the n plus I plus 1. Remember, xi bar is 1 minus xi, and product 1 less than equal to I less than j less than equal to k again. 1 minus xi xj, somewhat like the one there, and 1 minus times 1 minus xi bar xj, where, okay, this 5k of x1 up to xk is this sum over permutations in sk and subsets in 1 through n of minus 1 to the inversion number of sigma plus the cardinality of s, an operator g sigma s acting on product I equals 1 to k xi bar to the k minus I xi to the k, and product 1 less than equal to I less than j less than equal to k, 1 minus xi xj bar, 1 minus xi bar xj bar. Okay, what is this operator? So it's really a horrible expression where g sigma s acts on formal power series in x1 to xk, right? This is a formal power series by first, I should not write one, replacing xi by xi bar for all I in S. It depends on both sigma and S, and then replacing xi by x sigma I for all I in 1 through n. Okay, so it's a really horrible expression. And so the third part is proving that both constant terms are equal. Then so notice that he has not enumerated nk-magog or nk-gog trapezoids. He has shown that both of these are equal to these constant terms respectively, and then he has shown that the constant terms are equal. And all these are non-trivial steps. So in the last, I'm running out of time, but let me tell you a little bit about the story of the proof, because that's itself an episode. So he finished his proof sometime in '93, and then he submitted his proof to. So this was a massive proof, about 90 pages or so. And it was divided. He had organized this proof into like many lemmas and sub-lemmas and sub-sub-lemmas and so on. And I can stop sharing. So he submitted this proof to the Electronic Journal of Combinatorics, and the referee started. So the referee worked on it, and so there's hierarchy of lemmas, many of them. And he organized it as sub-lemmas and so on, 1.1, 1.2, like that. And he found that so the referee found a mistake in one of the sub-lemmas, and then he sent it back to him, sent it back to Zeilberger. Then Zeilberger corrected it, sent it back, and then the referee found a mistake in another of the sub-lemmas, Then he sent it back again, and then he said that, look, I have better things to do in life. I can't keep finding errors in your sub lemmas. So now when you submit it, you better make sure that everything is correct. So otherwise I'll be very annoyed. So actually it turns out later on we found out that this referee was actually Dave Robbins, who came up with the ASN conjectures in the first place. So then Zeilberger hit upon a strategy. He emailed, so this was in the initial days of email. So he emailed his proof to about 90 people, and he requested all of them. He assigned each one of them only one sub lemma. Their task was only to check. He requested them to please check just this sub lemma, assuming everything else is correct, and to get back to him if they find any errors. So thankfully for for him, or not thankfully, good for him. Almost everybody responded. They all found errors. They either found errors and corrected them, or they found error, or they did not find errors and told him so, or they fixed the errors and they wrote back to him. And one person was assigned, I think it was Brasud, who was assigned to check the overall logic of the proof. And thankfully everybody did, and then he submitted it and it was accepted. And this you can see now in the Electronic Journal of Combinatorics, which is a free journal. This finally appeared in Fuata's birthday issue in '95. And he has, so if you it's interesting to look at the proof. So he mentions each one of his non-anonymous referees by name, and he, at the end of the proof, he writes a couple of sentences for each one of his referees. So almost all 90 of them, and he says something nice about them. And so this is the story of the proof of the alternating sign matrix conjecture. Okay, so I think I'll stop recording now, and